Welcome back, guys, to another video. In this lesson, we are going to cover calorimetry and do a quick review of the calculations for water within the heating curve. So what we have here on screen is some data that was obtained from a lab. And in this lab, what we pretty much did was heat up the metal and drop it into some water. Now, here we have a visual, and we know that since the metal was heated and the water was at room temperature, so roughly rough temperature, it's stated here 24 degrees Celsius, we know then that the temperature of the heat of the metal was transferred into the water. So what I'm saying here is, in this visual, is that whatever the heat that was stored within the metal was released to the surroundings. So that resulted in an increase of the temperature of the water and a decrease in the temperature of the metal. Now, we are told that the mass of this metal was 50 grams, the water volume was 200 milliliters, the initial temperature of the water was 24, and the final temperature of the water was 26.5. And I should say here, it says final temperature of the water, but because the metal was introduced into the water, that actually represents also the temperature of the metal, because we have the idea of thermal equilibrium. Eventually, both the metal and the water will have that final temperature of 26.5. This question is asking you to calculate the specific heat of the metal if the initial temperature of the metal was 87 degrees Celsius. So this is where we need to learn how to use a calorimetry idea. So what's happening here is our understanding that whatever energy is gained by the water must be also the same energy that was lost by the metal. So the way we answer these type of questions is that we start with the water. And the reason we start with the water is because we have all of the information we need for water. So we are going to use the equation Q equals mc delta T, where Q is going to be the energy, the heat absorbed or released. Mass is going to be given in our problem, which in this scenario is 200 ml of water. The specific heat of water, because this is liquid, we already know from previous lessons that it is 4.184. And the change in temperature of the water is given to us here on the table of data. So that would be final minus initial, and that is going to stay true throughout this lesson. So 26.5 minus 24. All right, so then what we would do at this point is get a calculator and input this exactly as it's shown here. So we would do 200 times 4.184 times 26.5 minus 24, because we want to know the difference. So our answer comes out to be 2,092 joules. So what we're stating here is that the water gained a total of 2,092 joules. So now what we're going to do next is take that exact same number and start it and use it for the metal. Now the reason we're doing that is because if the water gained 2,092 joules, then that means that the metal lost 2,092 joules. Because remember, whatever energy was in the metal was released to the water. So it's kind of like somebody gives up the energy, somebody else gains it, and that amount of energy is the same. So what we're going to do now is utilize the information that we have for the metal. We're still using the same equation. So the mass that we're told of the metal is 50 grams. We don't know the specific heat, so we're looking for C, right? That's what the question asked us for. And then the change in temperature is final minus initial. And again, the 26.5, that accounts for both the water's temperature and the metal's temperature because they reach thermal equilibrium. And we are told in the problem that the initial temperature of the metal was 87. So whenever we solve for this, we're going to basically look for our missing variable. So we're going to simplify the right side of the equation and do 50 times 26.5 minus 87. And we should expect to get a negative number, right? Because we're losing energy here. So that would be 3025. We're still looking for C. This is why algebra is a prerequisite for this class because we need to know how to solve for missing variables. So we are going to divide both sides to get c by itself. We do to one side, we do to the other. And now what we're going to do is divide our two values here on the left side of the equation. And we end with an answer of 0.692. And that would be in joules per grams times degrees Celsius. So this is our final answer. And if we had a table with all of the specific heats of metals, we would be able to identify or find the one that's the closest one to this value. So you would look at the chart, see which one matches or closely matches, and then that would be the identity of our metal. So calorimetry examples are pretty much the same. The only thing that changes is going to be the temperature and the masses. So, and honestly, you could use calorimetry to pretty much identify and figure out the specific heat of just about any substance, because we can depend on the fact that we know the information for water, and then we can go from there and figure out our specific heat. Now, let's go and look at the phase changes within the water and the calculations for heat. So some things that we need to remember, there are three different equations. One we use for freezing, right? Freezing. Oh my gosh, my screen is not picking up my writing. Freezing and melting. Another one, the second one, we use that for vaporization and condensation. And the last one we use always for solids, liquids, or gases. So it's important that we understand that, because a lot of the time students want to use the wrong equation, and that will obviously give you the wrong answers. So when we talk about the specific heat of water, that is dependent on if it's a solid, liquid, or gas. So just make sure that when you're inputting the values into the calculation, you're using the correct one. So let's look at an example right here, and for your convenience, I put the information here as well on the bottom right side of the screen. And let's read the question. We are told that we have a 350 gram block of ice and it is removed from the freezer. The temperature of the freezer is negative 15 degrees Celsius. The block of ice is placed in a container and allowed to come to room temperature of 75 degrees Celsius. Calculate the amount of energy absorbed. So what we're going to do here is going to be just for visual purposes, we're going to draw our heating curve. So we know that we're starting as a solid and eventually, right? So we're going to go from negative 15 up to 75. Notice here how we never reached, my numbers aren't aligned to the heating curve, but that's okay. We get the point here, that we're moving from negative 15 to 75. So basically what I'm saying here is that we started as a solid, went through melting, increased all the way to 75, and then we stopped. So we never reached the boiling point. So in this scenario, we are only looking at three sections of the graph. We're looking at the solid, we're looking at the melting, and we're also looking at the liquid. And just like before, I want us to think about the different sections as your own little equation. So for solid, we are going to go from negative 15 to 0. Through melting, there's no change in temperature, just like we learned previously. And for liquid, it's from 0 all the way to 75 degrees. So what we are going to do here is we're going to use the correct or the corresponding equation. So I'm going to do it in a different color. So we're going to have the mass, which is going to be 350. And I'm going to then utilize the specific heat for solid water. So that's ice, right? So that would be 2.09. And I have those values here on the bottom right side of the screen so that you can see them. And then we're going to look at the difference in temperature. So that would be final minus initial. So 0 minus 15, minus negative 15, I'm sorry. Then we will take the melting, and that would be from 0 to 0. So what we will do here, it will be utilize the melting equation, so heat of fusion. So that would be the mass 350 times 334. And then we're going to do the last one, which would be 0 to 75. So what that's going to be is 350 And because now we're talking about liquid, we need to use the specific heat of liquid, which is 4.184, and that's of course of water. Okay, that does not look like an 8. That's supposed to be an 8. And then the final minus initial temperature, so 75 minus 0. So we would get 3 different answers here, and then at the end, we would add them all together. So what I'm going to do is I'm just going to walk you guys through the multiplication and then give you guys the final answer. So for this very first one, and I'll do them in a separate color, this first one, we get 10972.5. The next one, 350 times 334, gives us 116,900. And then the last one, 350 times 4.184 times 75 is going to give us 109,830. So when we add up all of our values, we would expect to see a positive answer because this is an endothermic process, right? So our final answer comes out to be 237,702.5, and that is in joules. So the amount of energy that was absorbed by this 350-gram block of ice once it was removed from the freezer and allowed to increase all the way to 75 degrees Celsius was 237,702.5 joules. And again, one of the biggest misconceptions I see my students make is that they use the wrong specific heat down here. Just match it up to solid, liquid, or gas. And also sometimes they forget that they also have to account for the melting, freezing, condensation, and vaporization. So sometimes they forget to use these 2 equations. So just make sure that we keep track of that. And also, I think also that drawing the heating curves helps a lot so that we can visualize where in the graph we're actually working and which are the equations that we need. We need to do a little bit more practice, so make sure that we access that information in our class. But other than that, thank you guys so much for watching.